can tell me to speak slower if I speak too fast. I think we stop at 5 is the program, right? Yeah, so we'll stop. I think we'll get to 5 at least, so stop then. Okay. So we were talking about the first molecules detected in the visible. The diffuse interstellar bands couldn't be identified yet, and the first molecules detected in the visible which could be identified. So that's these 3 little lines. And so this unit, in this case, is wavelength. This is intensity, and it's angstroms. So that's, I think I put it on my list. An angstrom, 1 angstrom is 10 nanometers. So that is a terrible unit. We're trying to phase out angstroms because it's just unnecessary. Just use nanometers. In the future, only use nanometers. So that's 389 nanometers. So that's the visible. And it was seen looking at this object. In this case, we have an Ophiuchus star, not Zeta Ophiuchus, sorry, not Rho Ophiuchus from before, but Zeta Ophiuchus, which is a very bright star, and it's shining through this interstellar cloud. And this is quite interesting, actually, because the star here, and you can't see it too well, but this is like a bright band of emission here in the infrared. This is an infrared photograph. And that infrared is because that gas is being heated and emitting in the infrared. You have to be warm to emit in the infrared, the black body radiation, infrared. And it's because this star is actually moving that direction through the diffuse cloud that's producing these lines. So there's like a collision, a shock wave of the star moving through the cloud. And that's a perfect picture of an astrophysical shock wave. So that's kind of interesting. Okay, and the interesting thing about these molecules is that they're diatomics, which is the picture I was drawing mostly, 2 atoms. And that kind of makes sense because diatomics often have lines in the visible rather than the ultraviolet. And CH and CN, I mean CN, if we think of this bonding idea, CH and CN. So that's a triple bond. Nitrogen has 3 bonding electrons. That's a single bond. So we've still got spare electrons in both these cases. And so that means we have an unstable, or in principle on Earth, an unstable species. It's reactive. It'll react with other molecules if it collides. Because it's in a diffuse cloud, the collisions are so rare because the density is so low, then it doesn't react, it just survives for a long period of time, long enough to see it in here. So the interesting thing was that they were both radical species. And that wasn't expected. Why see radicals in space? That's what they saw. Looking at actually the same cloud. This is the same object, but not looking in the visible. This is now angstroms again. So that's not 960 angstroms, 96 nanometers. So that's deep in the ultraviolet. It was observed with the Fuse Space Telescope. And in this case, they're looking at the background light from the star here, and this wiggle, that shows the absorption in the stellar photosphere as a function of wavelength. So that's the stellar lines, kind of broad. And on top of that is some extra absorption lines due to H2, HD, and so D, that's the deuterium, that's hydrogen with an extra neutron. You could call it, I mean, the normal thing with isotopes is if you have carbon, you could really call it carbon-12, meaning that in the nucleus, you have 6 protons and 6 neutrons, a total of 12. The other isotopes of carbon are 13 carbon, where you have plus 1 more neutron. So that's the isotopes of carbon. Of hydrogen, you can have hydrogen, 1 hydrogen, or 2 hydrogen, meaning you add 1 more neutron to hydrogen, or deuterium, just in case you didn't know that. What we're looking at is an H2 molecule, 2 H2s, or an HD, an H, hydrogen and deuterium bonded together, and nitrogen, a weak nitrogen absorption line there. And the point of the spectrum actually was the nitrogen, because nitrogen is one of the most abundant molecules in space, as we'll see, but it has never been seen. It's completely invisible. The reason for that is because when you have these diatomic molecules where you have 2 nitrogens together, or 2 hydrogens together, or maybe 2 carbons together, you have the same atoms, they become almost impossible to detect. In this case, these were both 2 different atoms bonded together. That's why they appeared initially. So we'll get into that later. Okay, the point is that this is in the visible and the ultraviolet. You're seeing these electronic absorptions in diffuse clouds. The problem is if you go from a diffuse cloud to a dense cloud, so there's a lot more material in the line of sight, it's denser as well, then this is a visible light image of all the stars and a dense cloud in front, and there's nothing. It's completely absorbed. That's why it's called dark as well, dark cloud, another option. And, yep, thank you. And what that means is that you can no longer do absorption spectroscopy because you need to have a background with some lines absorbed out of it. If you absorb everything, you have no absorption to measure. That's the problem. The column density of absorbers is too high, the amount of dust. And so instead you look at the same cloud, and this is not visible, this is infrared radiation now, but it's been, each wavelength of infrared has been translated to a wavelength in the visible to make the graph. And then you can see through it again. And so what's a dark cloud in the visible becomes transparent in infrared. And that's the critical thing about moving from diffuse clouds to dark clouds. You can use visible spectroscopy to look at diffuse clouds, but that fails in dark clouds. I guess I should point out this is a reasonably old photograph actually, and so this is not really a color photograph. Instead, it's measured in 3 different wavelength bands, where they've if you look at the entire visible spectrum, wavelength, beginning at say 300 nanometers, going to maybe 700 nanometers or something. And if you look at the actual emission of a star, it'll be this kind of black body shape, like we saw. And then rather than photograph that with a color picture, you instead measure that in different regions. What are they called? B, P, and I. B, and so you're actually measuring not just a range of colors, but individual blocks, like the human eye. So it's a filter image, and so each letter corresponds to a different wavelength at the center of that filter recreated as an image, including infrared wavelengths, 800 and 2000 nanometers. That's what that picture is. Okay, and so the reason for the darkness and the reason why it's not so opaque for infrared radiation is because of the dust. I mean, everywhere in the galaxy there's dust, and it originates during the expansion phase of the old red giant stars. That after the solar system, the sun eventually becomes a red giant and produces a lot of material, including dust. This is a picture of one. This is an actual dust grain collected by a spacecraft from the Earth's orbit. So it's actually collecting dust grains that have been produced and pushed out away from the sun by the solar wind, and brought back to Earth and then observed with a microscope, so you can really see exactly what a piece of dust looks like from interstellar space. And this exact same stuff exists everywhere. So in the dense cloud, where you have this density of gas, you have a density of dust as well. And the point about dust is that it has a transmission function exactly like the atmosphere, except in this case, the transmission function has this shape. This is wavelength. This is microns in this case. So 1 micron here, that's about the beginning of the infrared. 0.1 microns, that's 100 nanometers, that's the ultraviolet. So the visible spectrum is in this region here. And so this unreadable scale, this is actually opacity. So that's the fraction of light absorbed by the dust. Not transmission like we saw before, but the reverse. So this point here, the dust absorbs all the radiation. The vertical scale is just made relative to 550 nanometers visible radiation. So the vertical scale is kind of relative. So at the shortest wavelength, ultraviolet, dust absorbs a lot of radiation. As you go downwards, increase the wavelength, it absorbs less and less and less. That's to do with the scattering properties of the dust, like we saw with the atmospheric transmission as well, with some features in between, and that's to do with the chemical composition of the dust. There's the fact that it's made out of certain kind of minerals with different absorption peaks, but we'll get onto that. The point is that as you go to longer wavelengths, the dust absorbs less radiation. So, longer wavelengths, the dust absorbs less radiation. That's the picture. Yes?
I wonder if that view depends on the density of the cloud.
Nope. Well, it doesn't in the sense that individual dust grains will always scatter dust regardless of their density. So you could have, for example, you could have a very large cloud with a low density looking through it, or a very small one with a high density. You should have the same scattering. Where it changes is that if a photon gets scattered by a piece of dust, hits another one, hits another one. So actually, the path of the photon can be very complicated, and if you start having higher and higher densities, the photons, they bounce around a lot before they escape. So that can change with extinction.
This is something statistical.
Statistical. Yeah. Indeed it is. To calculate that curve, this curve is fundamental. This is talking about the opacity of the fundamental microscopic properties of the dust. But
with the picture is more clear, less opacity. This figure, this graph, showed me that for visible wavelengths, the dust is completely dark,
yeah.
but for infrared is less dark
Yeah.
than for visible. So, as you say, the photons in infrared can't cross the dust more than the visible.
Exactly.
It's-
The light
it's just
shines
that.
right through it without anything happening. And that's
Okay.
exactly it. And if we consider that, consider that picture, the visible light is blocked at this point. The infrared from that image is BIK, so 800 nanometers, 2,000 nanometers. We have to translate that to microns now. So that's 2,000 nanometers, there's 2 microns, 800 is somewhere there. So we're in this part of the curve. So the opacity has gone down roughly 10 times. If we go to the submillimeter, the ALMA band at 1,000 microns, this is 1 millimeter, it's gone down 5 orders of magnitude. So you can see that you can see better through the cloud infrared. The submillimeter, there's no cloud. You know, that's the point worth making.
Could you please repeat what the y-axis stands for?
Yeah, yeah.
Duration to what?
So you can't see it, I realize that, but this is the opacity. Normally it's the symbol kappa, the Greek K, I guess. And what it's saying there is kappa divided by kappa V. And so V, V, 551 nanometers. That's one of the bands that people conventionally use for filtering visible light. So rather than put this on a scale where you have to have so much column density of dust or so much opacity, you just relate it to that one reference wavelength, which is the standard reference wavelength for extinction in the cell medium.
So what does it mean when that number is more than 1?
Okay, sorry, all right.
Greater than 1.
Yep. Opacity, yeah. Sorry, I should, it's a good question, I should have explained that. Okay. Say you have the situation where you have a star and you have an interstellar cloud and I guess a telescope or something. And so there's so much intensity from the star, which is a function of wavelength over here. And then after passing through the cloud, some of it's absorbed, there's less overall intensity. And so what we're interested in is the function as if you have a bigger and bigger cloud, how does this intensity decrease as a function of wavelength? And the decrease in the simplest possible theory, the first order theory, is exponential. So that that. The simplest possible thing is that the more cloud, the more photons get deflected out of the way. And you're saying whether it's statistical or not. I mean, an individual photon strikes a piece of dust and gets deflected. Another one gets deflected backwards maybe. And the point is that only the ones that go through to the telescope get detected. And if you're looking at a single star, any deflection will take you out of this line of sight because it's a very pencil line of sight. So the chances of a photon being deflected back into the line of sight is actually very, very low. The scattering into the line of sight is almost, except in the densest clouds, unimportant completely. So you can use this first order formula to describe the radiation. And the point is that if you just talk about the reference wavelength of lambda equals 551 nanometers, then rather than describe kappa in absolute terms, which might be uncertain, you can just describe it in terms of that one, which is what that graph is. So a value of 1 means the same amount of scattering as at 551 nanometers. A value of 10 means that it scatters more than visible light. UV light scatters 10 times more than visible light. Okay. Yes. Okay, so that's talking about absorption through a cloud. So the opacity reduces the absorption through the cloud in a wavelength-dependent way. That's not the end of the story, because there's not just absorption of starlight, there's also emission from the cloud itself. I mean, these clouds, if we go back to this slide I showed earlier, have a temperature of between 50 to 100 Kelvin, if it's a diffuse cloud. And so it's kind of like a very cold star. And so it has the black body curve of these units. Don't ask me about the units, this is just an arbitrary unit. We're looking at the functional dependence in this case. If you have an interstellar cloud which has a temperature of 100 Kelvin, it's just warm, well, it's cold dust, it's minus 200 degrees, but in interstellar terms, it's warm dust. Then it has a peak here at 10,000 gigahertz. So 10,000 gigahertz is well into the infrared. You can go back to the units page to figure that one out. The infrared spans, from about 10,000 gigahertz roughly to 10 to the 6. The submillimeter is more in the 100 to 1,000 gigahertz range. So if you have a 100 Kelvin cloud, that's this curve here, it has a peak in its blackbody emission in the infrared, and that falls down by a factor of 2 orders of magnitude by the time you get to the submillimeter. So not only are we seeing starlight shining through in the infrared, we're also seeing emission of the cloud itself. So there's two effects. If you have a very cold cloud, 10 Kelvin, and if you remember the very dense clouds, they can get that cold because they're so dark, there's no light penetrating, no energy getting in, they get very cold. That peaks at about 1,000 gigahertz, so that's now the submillimeter. So the very coldest material can be seen as blackbody emission by ALMA. The hotter material, you need an infrared telescope. If you want to look at a star, you need a visible telescope. Yeah. So that's what we're doing with the infrared. And if you look at this is the same cloud again that I showed 2 pictures of. Now we're looking at it in the submillimeter, in microwave wavelengths. Not with ALMA, sorry, with the Herschel Space Telescope. So, and indeed, what we're looking at now is the stars, where before we had stars everywhere are gone, because stars don't emit much light at this long wavelengths. But instead, the cloud itself is irradiating a lot of energy. And that's the blackbody emission from the cloud. And the other interesting thing we're seeing is the shape of the cloud is kind of make outable. This is the infrared image here. And we're seeing the cloud is not so uniform anymore. It's not just a homogeneous clump of gas and dust. It has internal structure. In fact, there's a lot of internal structure. It's clearly either a bit warmer in this part of the cloud and a bit warmer there, so there's more blackbody emission, or it's the same temperature and it has higher density because the emission is.
On this white lines is like a leveled map. It's of our density or
that is.
Yeah, it's of course. Is just the shape of the cloud. But why do you have different levels? Is density?
it's actually the emission, the extinction exactly, or extinction, the density of the cloud in the infrared.
Okay.
You can measure from the infrared. So it's showing you the shape of the cloud in infrared combined with the shape in the submillimeter, and they're kind of different because of this asymmetry. And there's other clump over here.
Okay, so it's like isodensity curves.
Yes. Sorry. Yes.
Okay.
So, I mean, you could draw the same color scale as, I guess, contours as well. This is infrared contours on submillimeter color scale. Yes. Right, so now we're looking at black body emission from the cloud, not just starlight shining through. Okay, what comes next? Yes, some astrophysics. As I said before, you have these giant molecular clouds, the biggest structures, and within those, dense cores form. The idea is that you have an interstellar cloud, and it's, as I said before, it's turbulent, it's mixing within itself. There's temperature gradients and velocity gradients within there. And within that cloud, you get extra high density regions because of the way that if you have two turbulent motions coming together, you get a high density region where there's a shear. Alternatively, it might just gradually become high enough density that its own gravity becomes important, and then it falls into itself in a runaway process, meaning that you have dense cores within the entire cloud. What stops the cloud collapsing immediately is gas pressure. I mean, it has a temperature, it has the ideal gas law is holding it apart. Also some effects from the fact that it is turbulent, so that's some energy from turbulence that prevents it from collapsing, or magnetic fields is another study of research. The point is though, in these dense cores, you get a high enough density locally that gravity wins this battle and it starts to collapse under its own gravity. And so you have these infalling into a higher density core within a high density core. That's what we're looking at in this picture, in that you have the general cloud, and in local regions, the density increases as it collapses further. But there's two cases that we're interested in. One case, it collapses and forms this really dense, cold clump. And the other case, it collapses and gets so dense that a protostar forms. And this completely reverses the process because suddenly you're having energy source within your cold clump, and it becomes a hot clump. So there's a real almost identical conditions, high density within a cloud, except one's warm and one's cold. That's hence the cold core and the hot core. That's an interesting difference. And we know in this case that we're seeing clumps in the submillimeter. And we know that submillimeter has a black body temperature of about 10 Kelvin, so the clumps we're seeing are about 10 Kelvin. And we know we're not seeing clumps in the infrared. And we know that the infrared has a temperature of 100 to 1,000 Kelvin. So we're definitely in this case. Otherwise, we'd see infrared emission as well coming out of this thing.
How do we know we're not seeing it because in the infrared? How do we know that none of those points we see are actually?
You mean, well, okay, that's a good question. I guess, you mean, are these stars or?
Like, yeah. Like I can
Yeah.
kind of tell that those are stars in the background, like behind the cloud, but can we actually say that's true? Can we say that maybe one of those points are actually
I'd say we can. I think I think that if you look at because I mean you can look at the spectrum of these points as well, and the starlight should show a stellar black body curve multiplied by this, whereas a clump will show an infrared curve multiplied by this. So the spectrum of those points is important. And I guess the other thing is that you could correlate those points with these emission in the submillimeter as well. So there should be a correlation between infrared cores with submillimeter emission around it. That might be the two ways to work that out. Okay, yes. Okay, so in that cloud I showed you, B68, I should have said the name, we're in this case. This case is the case in the Orion molecular cloud complex. Okay, so in the Orion is a huge region of giant molecular cloud, or complex of molecular clouds actually, and it's widely studied. And this image in the visible shows a similar effect. You clearly can't see through this thing. There's a lot of dust, opacity. But if you look at the same region in the infrared, you see a shining light. So this now is a clear symbol of a hot core, in that there's enough temperature from a protostar to produce infrared radiation. Yeah, and this we haven't talked about it in chemistry yet, but this is two really different chemical cases, because the temperature that you're having inside this core affects what molecules can react and so forth, and it also affects the spectroscopy. Okay, so this is a spectrum measured with Herschel. Actually, this was Herschel. This is the Space Telescope, and it's a spectrum showing the microwave, so that's the infrared radiation coming out of Orion. So that's pointed at one of these. I don't remember which one. One of these hot cores within Orion, possibly one of these three, most likely. I don't remember which one. Sorry. And so what we see here is, as a function of wavelength, you get a increase in this sort of background radiation. That's the black body radiation of the hot core. So you can estimate the temperature. If you account for the dust absorption, you can estimate the temperature from that. And there's many molecular lines shown on here as well. And rather than be absorption lines, like we saw in the stellar absorption, or absorption lines like in the diffuse cloud absorption and the visible, we now have emission lines within this, on top of this black body emission. And what are we looking at? Okay, so what we're looking at here is vibrational emission. If you remember the kinds of molecular motion, the infrared was the region where you have vibrational motion. So we're looking at, for example, these lines here, which kind of indicated not so clear, are vibrational lines of H2. Yes? Well, I mean, you could estimate the dust temperature, but I think that you won't really have a perfect black body. I mean, one temperature, because you have dust in the hot core, which is maybe a few hundred Kelvin. You have dust in front, between you and the hot core, which is colder, and on the edge, which is hotter again. So you actually have a complicated structure of black body you're looking at, but you don't need to, because these lines are very narrow. You just draw a line under the line. If you want to measure how strong the line is, you just subtract everything else. So in general, I think the way to measure the line strength is to just remove a continuum without a black body model, just subtract a continuum. That's best. Okay. I just wanted to explain this notation because I'm a spectroscopist originally, and we love notation. Okay, if you have the hydrogen molecule, thank you, with its vibrational levels, and if you have emission, that means you're dropping down in energy. You're releasing energy, so you have to decrease the vibrational numbering, and a photon is generated. And so that has a notation, in this case, of 1 to 0, that process. And so this entire series of lines here all have the number 1 to 0, so that's that particular vibrational transition. There's another series of lines 2 to 1, so that's that series of transitions, this one. And the reason there's more than one of them is because you also have rotational levels here as well. And you could have transitions between different pairs of rotational levels. And so that each vibrational transition will have multiple rotational transitions, so that actually vibration and rotation aren't separate, they can go together. And that's the point I wanted to make. Okay, so now we're directly observing molecules in the infrared in a warm cloud, and because it's warm enough, they appear as emission lines because of the high energy.
Again, so the number in parentheses represents
See, this is the only problem with the field of spectroscopy, is that it's obsessed with quantum numbers and notation. Okay. If you think of one particular transition, H2, and we're going to go from V equals 1 to V equals 0. And we're also going to decrease in rotation. And rotational numbers are given the letter J. And say we went from J equals 2, J equals 1. So that's from here to here, from number 2 to number 1. So that specifies that particular. So then we give that the label 1 to 0, meaning 1 to 0, and then another symbol. In this case, it's going to be R1. And 1 means this one. The lowest rotational level is put in there. And the R tells you about the change in J. In this case, J has gone from 2 to 1. So the change in J equals 1. Fair enough. You could alternatively have a transition from 3 to 1, and then that would be equal to 2. You could alternatively have a transition which was the same rotational level, minus 1, so forth. And then rather than write minus 1, 2, 0, 1, instead we call that Q, that R, R and S. So, and O above P, O, P, Q, R, S. Yep. Okay, so J, I mean, we know that V is the number of the rotational level. It begins at 0 and just goes up and up and up, like quantum number n for an atom. J is the number for the rotational levels. So this first rotational level there, J equals 0. The next one, J equals 1, up and up and up. And the same thing happens here for the actual level. So we're interested in the change in rotational level like that. And so that can be, if delta J equals minus 2, we give it a letter. So in this case, 1, 0, vibrational level 1 to 0, R1, delta J equals plus 1, the bottom level equals 1.
So,
fantastic.
1,1s transition is just a rotational transition.
Yes, exactly. Yes, precisely. Yep. It's within the V equals 1 level itself. Yes, good. Yep. Yep. So yeah, so there is some pure rotational transitions in this spectrum as well. I mean, when I said rotational spectrum is microwave, vibrational is infrared, yeah, that's mostly true. Let's not get too hard and fast with these rules. And this you'll never see in a cold core because you wouldn't have enough energy to excite these excited levels to show vibrational transitions. But we'll get to that later. Because there's something else interesting on this graph as well, which is this point, and I guess this point, and that point, where we have dips. So there's also emission going on as well as absorption in the same spectrum. And it's not stellar absorption because the stars are completely obstructed by the dust and in the infrared. So that's actually to do not with molecules floating around in the gas phase, but molecules in the ice phase. Because there's dust everywhere. Another picture of a dust grain, also recorded in the solar wind. This says 1 micron, so this entire dust grain is maybe 1 millimeter big. And this is not representative of the dust grain you will find in Orion or in other interstellar clouds, which are much smaller. This is 100 nanometers. The entire dust grain is less than 1 micron. So, it's completely tiny. And actually, there's no lower end to these dust grains. we could draw another graph showing the size, the frequency of dust grain size, and it goes all the way down to molecule. So that a very small dust grain is really made up of 1,000 atoms. It's basically a molecule. All the way up to one that's a millimeter big. It's clearly a piece of dust. So there's spectrum there. But anyway, so these dust grains are made of graphite and silicates. Silicates, the same as most rocks on Earth. Graphite is mostly carbon material, and other kinds of carbon silicate compounds, there's all kinds of stuff in there. And the part that we're looking at in this spectrum, though, is on the outside, where if you have a cold enough environment, the gases will freeze onto the dust grains. That's like exactly the same as nucleation of rain or snow. And so if you have a case, say you have an interstellar cloud. This is the edge of it. Go away. This is the edge of an interstellar cloud with a telescope observing over here. And over here, you have a hot core. So T equals some hundreds of kelvins. And so we know that there's a black body irradiation from this hot core going this way. But in between, you have the rest of the giant molecular cloud, which is much colder. Let's call it 10 to 20 Kelvin. And so it's here that we have dust grains with ice layers. So in this case, the hot core is giving a source of infrared radiation, but it's the dust grains in between the hot core and the observer that are cold enough to have these ice layers. So what we have H2O, water ice, CO2, more H2O, and so forth. But if we look at this in another spectrum, this one's a different interstellar cloud. A real astronomer would study. Nope. Yeah.
I want to know if the opacity graph that you show us later depends of the size of the dust grain that is in the interstellar cloud.
Yes, it does. And it depends not just on the size, 100 nanometers. It depends on the shape of the curve, because it's a distribution of dust grains. I mean, really, size, 1 micron, 10 nanometers. I mean, you have kind of a power law shape of all kinds of size dust grains. And it depends not only on that, it depends also on the geometry of the dust, whether they're kind of elongated or spherical or kind of, in fact, you can see here, it's neither. It's made up of, a dust grain is actually made up of smaller dust grains stuck together. And in fact, if you stick these together, you get a bigger dust grain. Eventually, you stick enough dust grains together, you get a comet and a planet, ultimately. But so this kind of structure, yeah. But yes. And the way that we can draw this picture and say this is 100 nanometers big is by looking at the extinction. I mean, you can actually use the extinction to constrain that distribution of dust grain sizes. That's actually the way it is. Okay. Okay. Right, okay, so I apologize, this is a change of interstellar cloud. It's not Orion anymore, but it's the same idea. With a hot core, this graph shows the infrared emission. So you have kind of a lot of dense cloud and in a couple of regions where you have extra dense clouds, and that's where the protostar is about to form. That's the hot core. And if you look towards that point with an infrared telescope, this is with I think this is with the ISO. This is an older infrared telescope that first made these measurements. Then you see the black body radiation and deep absorption. There's a lot of ice in front of this hot core. And the ice is made up of silicates, so that's the molecules that make up rock. I won't worry too much. A lot of silicates. It's got a deep water line. So this silicate is the dust itself. This deep water line is the ice around the dust. The radiation goes right through the entire dust grain. More water, you have CO2 forming on the dust grain. You have methanol. Turns out methanol is one of the most abundant molecules in ice. I mean, which is kind of strange that you should have methanol, quite a complex molecule, appears in ice. CO2 makes sense. Carbon monoxide also freezes.
Methanol is CH3O4H.
Yes. Methanol, yes. Yep.
And what is HCOOH?
Formic acid. We can call it HCOH if you want. No, formic acid. The or formaldehyde? No. Yeah. 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 So that's an interesting one. Ammonia. And a question mark here, but it's been observed elsewhere. That's definitely been confirmed. 13 CO2. Does anyone what does the 13 mean? Isotope, exactly. So it's the same as CO2, but there's one more neutron on the carbon. So that's strange that should appear. In this particular case, the fact that this is a very weak line, it's a very strong line, just tells us the amount of 13 carbon that there is relative to the amount of 12 carbon. Formic acid, OCS. That one's really strange, because one thing you might notice here is that a lot of these molecules is an oxygen atom with hydrogens attached to it. In the case of CH4, methane, you've got a carbon atom with hydrogens attached to it. In the case of ammonia, nitrogen with hydrogens attached to it. In this case, we've got 2 non-hydrogen atoms together, but 3 non-hydrogen atoms together is actually a really unusual thing. The reason is that, we'll talk about this day after tomorrow, I think, is the most common element is hydrogen. So generally things just have hydrogen in them. So this is actually a real surprise. Not just that it's hydrogen, but it's also a negative ion. So you end up with an O, a C, and an N. I guess they're double bonded. And we'll do this again. If you recall, nitrogen has 3 bonding electrons, but in this case there's only 2 bonded to carbon. So this is technically a radical species. It shouldn't exist for long because there's an electron to react with its environment. Not only that, the entire thing has 1 more electron attached to it. So this is extremely unexpected to find this kind of thing. It turns out after researching it that this actually is a stable product in an ice, but that was completely unexpected. Yeah. So this is, I guess, another phase of matter in interstellar medium. Everything else we've talked about before is gas phase. Now we're in the ice. Okay. So that's looking at the infrared. What if we look at one of these hot cores in the submillimeter? This is not ALMA. I have very few ALMA results, I'm sorry. But this is what you would see if you looked with ALMA, or in this case with Herschel. So now frequency is in the units of gigahertz. Remember, that's the submillimeter units of preference. And this entire spectrum shows a background. In that case, I'm not actually sure. I think in this case, that's not black body, that's instrumental background. I could be wrong about that. But the point is that you see a forest of lines. These are all emission lines from the pure rotational transitions. So this is not, I've rubbed it out. This is not vibrational transitions with some rotational effect. This is just the molecule rotating in the ground vibrational effect in the microwave radiation. And the beautiful thing about this is that this is really where you see molecules. I mean, these other things were interesting, but if you look in the submillimeter, that's where you can learn the most about chemistry. And it's obvious if you look at the spectrum, where you see lots of lines in emission and lots of noise. You look at the noise, and there's more lines. Like, there is no noise, in fact. If you look at this noise, you get to the spectrum. And finally, there's a little bit of noise. Maybe those are lines as well, we don't know. Finally, a little bit of noise, this is just lines within lines within lines. And I won't go through this list, but there's 20 molecules here. If you look at the entire spectrum, it's more like 50 or 100.
Which is the problem with this empty lasers?
Yep.
You see that there are some special
Yep.
wavelengths without information.
Yep. So I mean, what I suspect was that it's not there's no reason. I mean, you can observe the cloud at the full range. The transmission is fine because you're in space. But there were multiple instruments on Herschel. Or it might have been the same spectrometer with multiple detectors. Part of the problem with working in the microwave radiation is each photon has so little energy that you can strike a detector and it's actually hard to efficiently detect it. So it could be that the detectors they were using weren't sensitive in those ranges. I'm not sure of the technical details.
I was thinking
Remember, the gift wasn't a solid promise. That was just a possible gift. Oh yeah, and I drew a picture of methanol. It's like a methane, a carbon, and except now you've got an oxygen and another hydrogen attached to it. And this is a really unusual case. This is a good molecule because I should say first of all that in this region we have all these lines marked in red, and all those lines are due to methanol. So, and there's you probably can't see it, but there's methanol lines throughout the spectrum. And the thing that's interesting about that is that most molecules, the simple ones at least, let's say carbon monoxide, it kind of rotates like this, spins around. It might spin faster, in which case we might have its higher and higher J levels, so that's just how we notate the spinning faster and faster and faster in a quantum way. Methanol can do that as well. The whole thing can kind of spin, or this particular part here can spin around on its own. In the sense this bent hydrogen is like a little propeller inside the molecule. And what that means is that you get a really complicated spectrum with lots and lots of lines, more than if you just had a simple rotating molecule, which appears throughout the spectrum. And that's kind of what makes methanol special, is first of all, it appears to be abundant, it exists a lot, and then it has that property as well. Yeah. Yeah.
When you say for a particular wavelength, you say, okay, this is this molecule with this bidirectional whatever, and where do you get the information? Are from observations or from theory? You know?
Yeah.
And also how, I mean, that's a mess, you know. It's yeah, you know.
Yeah.
It's,
Yep.
how do you know that's right? You know,
Yep.
okay, say that's a molecule and this emission of a particular molecule, and you say, okay, it's that molecule is in there, and you say, okay, I'm pretty sure to say that, you know.
Yep, that's the first job for observational astrochemistry, is identify what your lines are, exactly. And the answer to your first question, it's most of the results come from recreating this environment in the laboratory, like pure methanol. Measure it, experimental work, yep. I mean, once you've done some observations, you can extend it with theory by kind of studying the molecule in one part of its spectrum. You can extend it to the others, that works pretty well. But a pure theoretical calculation, generally, because I mean, to know you have the right molecule, it has to be in exactly the right place to line up with these lines that you observe in space. A slight shift, and you're not sure if it's the right molecule or not. So theory is not quite accurate enough. So they're experimental results. And you are then asked, there's so much stuff, I mean, how do you even begin to deal with it? What this graph shows is that if you zoom in on just one part, you see these lines, right? And even without knowing that it was methanol, you see something's going on. This is not a random selection of lines. And so that's a great place to begin. You know this is one molecule because something is making them the same shape. There's this clear increase in intensity or whatever, which is a classical picture actually in rotational spectroscopy. Yeah, well, I have another slide later, show some other ones. I mean, this stuff, I don't know. I think a lot of experimental results get put into a big database. You can compare that with your observations and automatically try and find them. Where problems start, actually, is okay. This one you probably can't see yet. That says HCO plus. Okay, so this one is strange because it has a positive charge. One electron is missing from the molecule. So that makes it reactive with its environment. We can do the thing again, but it's also a radical, so that makes it reactive with its environment. So it's a molecule that doesn't really stay stable for very long, which means it's a real problem to study in the laboratory. Studying radicals in the laboratory is kind of an issue. Methanol, you can buy it if you buy cheap liquor, I guess, and you can study in the laboratory. HCO plus is more of a problem. So those molecules are the ones they had to do specific experimental studies in order to find them in the observations. Anyhow. Okay, so what was my main point? My main point was that we looked in the visible, we saw a few lines. We looked in the infrared. We saw a few emission lines from H2 mostly, which was interesting, but yep. We looked at absorption in the infrared, we saw ices. So that's kind of interesting. We look in the millimeter, we see, a lot. That's where it's at with these molecules. Okay. All right, and so I said, somebody asked earlier on, what are the important parameters? And that was the density affecting the chemistry, the temperature affecting the collisions between molecules, and the UV. And so now we'll talk about that. Okay, so this is one of the most famous images. I think you might have seen it before, the Horsehead Nebula. In this case, the horse is on its side, sticking out of the thing. But that's it there. And what this image is showing is a dense molecular cloud over here. Goes on. And if you draw the edge of it, it actually forms a giant, some kind of circle. And that's because there's an O star about this point, which is irradiating so much energy, high energy photons, it's blowing away all the gas around it. So this the pinkness is actually, that's an image of the ionized hydrogen, H+. So in this case, there's so much energy from the photons, the hydrogen has its electrons stripped away and leads to ionized hydrogen. And that's striking into this face of this molecular cloud and actually pushing it away over time. But one part of it, due to hydrodynamics, is then being ejected back into the bubble. It's kind of like a turbulent flow which leads to that edge. So what you end up with is a very hard edge of an interstellar cloud being exposed to just a lot of radiation on one side. That's a really interesting laboratory because we can see how radiation and dense material interact at that point. And this is the simple model picture of what happens. So we have the really bright star, and this is the cloud. And in this edge part, we have a lot of photons, and it has a special name, photodissociation region. That's worth remembering because this is one of the most common kinds of chemical environments wherever you look in the galaxy, or extragalactically. And the main effect of the UV radiation is that it breaks up all the molecules. I mean, I won't write again. If the binding energy of the molecules is about 3 to 5 electron volts, then you need about a 200 nanometer photon to break apart the molecule. And this star provides enough of those to destroy all the molecules, meaning that at the edge of this cloud, this PER, this photodissociation region, you have only atoms. And as you go further and further in, because of the extinction due to the dust, the UV radiation intensity decreases, and eventually you can form molecules again. So you have a gradient of molecules on this edge. Another effect is that not only are you breaking molecules apart, you're also ionizing things. You're releasing electrons. So there's a lot of electrons in this part of the cloud. It's kind of interesting. Another effect is that we have these ice layers on top of the grains. The UV photons can hit the ice layers and knock molecules off the ice layers. So we're not only destroying molecules, we're also releasing molecules from the ice phase into the gas phase. That's another effect. This final point, I guess I'll make, is that you go deep enough into a cloud, all the UV is destroyed by the opacity of the dust, same as we saw before. However, that's not the only kind of radiation in the universe. There's also cosmic rays. I mean, cosmic rays are extremely high energy charged particles, protons, and other nuclei of other kind of atoms. Pure, like for example, you can have an iron nucleus with no electrons at all, just an iron nucleus, ferro. And I don't know. The point is that these have so much energy that dust doesn't attenuate them all. So there's actually a source of energy even within the deepest part of the cloud. There's no UV photons, but there's radiation and cosmic rays. I say that now because I'll say it again later. That's just to get you that into your mind. Okay. The main point is at this point. What's going on here? Okay, so the Horsehead Nebula was studied in the infrared and the far infrared and the submillimeter. And this is showing a graph of that exact Horsehead Nebula. This shape is exactly this shape. We're looking really at this point. And all the radiation is coming from this side. So this red line shows the edge of the photon association region. And all these different graphs show the density of the emission lines, how strong the emission lines are of all these different molecules. So this is taking all the spectral lines in a giant field of grass, picking one line to represent each molecule, and then making a map about how strong that line is everywhere inside the Horsehead Nebula. Okay. Any questions about that before I go on? Yes?
I wonder if it's possible to distinguish between a molecule and its isomer
Yep.
by the spectrum.
Yes, that is fine because the thing that just where the lines are, and this is actually in the next lecture, but whatever. Why not? No. Okay, let's think of one particular isomer that's kind of interesting. HCN and HNC. So it's not much different, just which atom is in the middle. And the rotational energy levels depends mostly on the rotational inertia of this molecule. So the length of these bonds, which varies between the molecules, changes the rotational inertia and therefore changes the energies of the rotational levels and changes the spectrum completely. Like that part is fine. Yeah. Okay.
What about the left-handed and right-handed isomers?
That you can't do, because in this case, all the rotational inertias are the same.
Oh my God.
Yeah. There was, I think the first ever chiral molecule was detected 2 weeks ago, 3 weeks ago. But, so the chiral molecule, I describe it. Sorry? What's the simple one? No, it wasn't amino acid, no. So in this case, it's the left or right-handedness of molecules. Chiral, yeah. 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 Yeah.
It's not related with life.
Yeah. 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 So they have detected the first chiral molecule ever to be seen in the stellar medium. The problem is to detect the ratio of the two chiralities, you need a polarization measurement and a polarized light source. And there's no good suggestions for how to do that. Okay. Okay.
So we think the Horsehead, next when we think the Horsehead, we need to dig in metal, right?
In what, right?
Metal.
Yes.
And we think metal next time when we think the Horsehead.
Yeah, exactly. Yeah. Go on. Okay. Okay, so what? Yeah. There's 5 minutes to go. Oh, it's 5 now. Shut up. Yeah, I mean, yeah. Okay, well, let's do this one. This one's pretty tough, but then because the next one is kind of a good place. Yeah, exactly. Yeah. So, yeah. So there's two important things happening which we can actually see in this graph. If you know a few things. The radiation is coming from this side, and it's destroying molecules. There's so much energy it breaks the bonds between atoms. and it's striking the ices and releasing molecules from the ices, those two things. And so we will in fact begin with methanol, because one of the main parts of ices is water and methanol. And so what's happening here is that as you approach this line where the UV photons are, you get a big front of methanol, and that's because it's been released from the ices by the UV radiation and the rising temperature. Then, combined with that, you also see H2, DCO plus C2H. And so what these are, this is the methanol being broken apart. So the methanol gets released from the ice and appears, and then gets broken apart by the UV photons, dissociated, and that produces these other stuff. This is an interesting case, H2CO, that's formaldehyde. In this case, this molecule doesn't come from methanol. It just exists in the gas phase by itself. That we can talk about later. So you can see that formaldehyde is not on this front like these ones are. It's everywhere, and that's because it's its own molecule, whereas methanol is creating these ones. CF+, I don't know anything about. That's just, and that's where, yeah.
Which means the size of the circle in the left corner.
Yep. So
Yeah, it's about the size of the molecule or something?
nope, it's the beam size, because all these molecules are observed at different frequencies,
Okay.
and maybe you can explain this to us later, but the telescope has different spectral resolutions at each frequency because of the wavelength changing size.
Ah, okay. So do you say that this morning?
Yep.
And other question about the figures. This white lines is related with the 3D shape of the cloud or something?
It's because they had, here I've said the Horsehead Nebula is like a flat surface facing this radiation. In the actual paper this is from, they had a more complex model. See that there's this, the front is not straight, it's kind of bent.
Okay.
And they have some other regions where they thought there was high density material maybe poking out of the cloud also. So there's kind of other modeling.
Okay.
And yeah, well, let's unless there's another question, maybe that's a good place to stop.
Yeah, so
I don't know. I've right.
So just wanna-
I made a list of questions and I was going to ask you guys which ones were the right ones. I don't know.
no, I just wanted to say that
Not too hard.
the beam is showed in the left down corner, which is what is usually shown in every radio image. You have to put the beam size. It's usually you put the beam size in one of the corners, usually there, to show your resolution. So this is your resolution, and it's your pixel size. So in every radio image, they show the beam. So this is your resolution. So depending on different molecules have different resolution. So the top left one is the best one, right?
Smaller is better, yeah. Yeah. Although you can see what's wrong with smaller here, though. In this case, there's such a small beam, they had to like point at many places to draw the map, and it took too long to do the whole thing, so they restricted it. Yeah. It's over. Applause.
Okay, so, entonces, mañana nos vamos a las 9, pero ya entonces vamos para el laboratorio. Right? Tomorrow is lab time, right? We will be...
Not for me. For me, I'm back here. Yeah.
Okay. So, en la mañana nos vemos en el laboratorio, está a las 9.